All right, and finally, let us talk about some practical considerations in machine learning. So I'll give you an example, right? So imagine that we constructed a very nice, very accurate model to predict stock prices. Right? So this is the real data of how SP 500 prices changed over the 1 year. So suppose that it's very accurate and we want to, so we are prepared to earn a lot of money. But then we deployed it in February 2020, and we had this because of COVID-19. So what happened? We lose a lot of money. And the reason is very clear, right? So because we trained it on this data, but we wanted to apply it to an unseen data. And of course, if this is the data that we have, how can it predict something that we have not seen? So the ultimate goal of any machine learning algorithm is to make predictions for unseen data, right? So it doesn't make sense to build a model that is able to accurately predict the data that we have, right? So it responds for the data that we observed, that was used to construct the model. So which is why in practice we always, so if we have a lot of data, so we split it into two parts. So training data and test data. So we only use the training data to construct our model. The test data is set apart. So the test data is here to simulate the unseen data, because the test data should not be involved in model construction at all. So we train our model, so we construct our model based on this training data, and then we just apply it to our test data to see how accurate the model is. Sometimes there is also validation data, but I'm going to talk about it later. So the process of constructing or fitting a machine learning model is referred to as training. Right? So training a linear regression means choosing the values of parameters that are most consistent with the training data, which most of the time means minimizing the mean squared error. So training a KNN, well, basically it doesn't mean anything. So if we fix a KNN, if say we know that, I don't know, K is 7 or something, right? So if we fix the value of K, then training a KNN with K equals 7, that doesn't really mean anything. So we just choose our training data set, that's all. So then the model is ready. So it is more complicated to apply the model to a new unseen data, but training is kind of trivial. So here is an example. So this is our advertising data set. So we are going to split it into training and test data sets by choosing training observations with probability 0.8, right? So every time, so we go through all observations. So we look at this observation, we throw a dice with probability 0.8, right? So with probability 0.8, we include it into our training data. So then we throw dice again, maybe we again include it into our trained data. But if the dice rolls out like a no with probability 0.2, then we do not include it into our training data. So which means that this goes to train, this is going to test, and so on. Right? So what I did, I kind of rolled the dice for every one of our 200 observations with probability 0.8, and approximately 80% of my data went into the training set, and the rest went into the test set. So you can see this here. So this is approximately 80%. This is approximately 20%. How to do it in practice? You will learn in the first lab session on the second week of the semester. So what I did, I trained a linear regression and KNN, 3 KNN models with K 3, 5, and 10 respectively. And I reported the mean squared error on the training set and the test set for each model. So notice that in all the cases, the training error is less than the test error. Is less. And this is, of course, the typical case because it is harder to predict an unseen data than to predict the seen data that was used in the construction of the model. Now, what is a validation data set for? The idea is like this. So if we want if we train a k and n model with a fixed value of k, like if k equals 7, then there is no validation set. But if we want to try all possible values of k and choose the best one, then this is going to be somewhat like training, right? So which means that we shouldn't use the test data for it. At the same time, we cannot just try all different values of k for the whole training data, because then if you think about it, then if k equals 1, then the error on the training data is going to be just 0. So it doesn't make sense to even try. So we somehow need to, if we really want to try all possible values of k, then we need to split our data set into 3. So the first is the training set, is where we used to train our model. Well, for k and n, it doesn't really mean anything, so we just kind of choose it. So then we use this validation data set to find the error on the validation data set. And then we choose k that yields the smallest error on the validation data. So this is what it looks like. So I did it for our data set, for advertisement data set. So notice that the training error is just increasing with k. This is typically the case. So when k is 1, then the training error is 0. This is always the case. So which is why, especially for k and n, we don't really care about the error, the training error. Right? So what we really look at is the validation error and the test error. So let us look at the validation error. So the smallest validation error is, I believe, here, which means that k is 11. So remember that at this point, we have not seen the test set yet. So what we do is we just find the validation error for all possible values of k and pick the best one. And then the test error is kind of the independent estimate of this validation error. It's going to be, of course, bigger than the validation error for the best one. It's not always bigger, so sometimes the test error, like here, I don't know, the validation error is bigger than the test error for some other values of k. And notice that our value of k11, which seems to be optimal for the validation error, is not best for the test error. Right? So the test error is the smallest when k equals 3. So which is why it is kind of wrong to look at the test error, because picking the value of k that minimizes the test error is something like training. So we shouldn't use the test data for our training. Okay, so now linear regression has parameters whose values are found by some clever algorithm based on matrix multiplication that you should know how to do it from regression analysis. In the next lecture, we will review this algorithm. So KNN has, as opposed to parameters, so KNN has a hyperparameter k. So the difference is somewhat subtle. The difference between parameters and hyperparameters is that so hyperparameters can be fine-tuned, can be found, the values of hyperparameters can be only found by trial and error. So this is what we did, right? So we just tried different values of k and compared and found the best. So, and a validation set is used when we have hyperparameters. which is usually the case. In future, you will see that usually we do have some hyperparameters, and we need some kind of a validation for our model. Now, so what we do is, and this is a bit kind of naive method, but what we did here is we split our set into 3 parts. So training, validation, and test. So we tried different values of k on the training error. So then we picked the best one, the one that yields the smallest validation error, so which was k equals 11. But then what I didn't do, but in practice it should be done, you then combine training and validation sets together into like a bigger training set, and then you retrain the model with the same value of k. And then you can report the test error. So this is kind of the best that you can do. But later we will learn more advanced methods of doing this in weeks 3 and 4 of our course. That there will be more advanced methods. Okay, so what is overfitting? So overfitting is like the curse of all machine learning. Is probably the most important issue in machine learning. So the most important practical issue. So here is a definition from Wikipedia. So overfitting happens when our model follows the data too closely. And this happens because if, so in theory, our y equals some function f of x plus some random noise. So what we want is to construct some f hat of x that models this f of x. Overfitting happens when our f hat includes the noise too. It tries to model the noise. And then, of course, the noise for unobserved data is going to be different, so which is why an overfitted model is going to poorly perform on unobserved data. So here is an example. So if the true model is a quadratic polynomial, so then a linear model, so the green one is underfitted. So the correct model is the blue one, is the quadratic polynomial, and an overfitted model is a polynomial of degree 10. And if you look very carefully, then the red polynomial is closer to our data point, has smaller training error than the blue model, right? So because most of the time, is like here. So the blue curve has a large error, but the red curve is really goes almost through these data points. So maybe just in a couple of positions, it goes a little bit far off the data points. But it is overfitted because imagine that if this is a polynomial of degree 10, right? So outside of this given area is going to kind of go very quickly to the negative side. So if our data point, next unobserved data, comes somewhere here, right? So our overfitted model is going to miss it by a lot. But even if our model is still within the same, well, if new unseen data is still within the same region, so maybe it could be here, I don't know, or here. So there is still a high chance that our overfitted model is going to miss it by quite a lot. So splitting the data into training and test sets is the simplest technique to deal with overfitting, right? So if you see that your model makes good predictions on the training data, but very poor predictions on the test data, it means that it is overfitted. Okay, a few other practical challenges. So one practical challenge is imbalance of data. So like think of a credit card data. So usually people do not default. So if say, I'm not sure, so this is probably like 80%, and this is probably like 20%, right? But if your model predicts that everyone is going to default, then your model is already going to be 80% accurate. So, and if if without knowing this background, you just say that my model is 80% accurate, it seems like it's good, but in fact it is not. So it just means that the data is imbalanced. So later we will learn how to work with imbalanced data. So another practical challenge is several data sets, and sometimes you need to merge them. So this is HTTP transactions and HTTP property information. So, and what you have is, if you have transactions of HTTP, so well, some HTTP flat under this address was sold for this amount of money, then if we want to see if some properties of the building, so like how many floors it has or how many units it has. So if it is related to this resale price, then we somehow need to merge this, so to insert this information into this data set. So this is a small practical challenge. We will learn how to do it in our computer labs. What happens if data is not in a tabular form? So the classic example is a text, right? So text, how do we convert a text to a vector of features? So x1, x2, x3, and so on, xp. Well, we will learn how to do it in our class, and in particular, in the end of our course, there's going to be a very good method of doing this. It's called GLOV, Global Vectors for Word Representations. Very fresh. It was invented just 6 or 7 years ago. Very, very nice and very, very beautiful mathematics. So this is something that we are going to do in this course later. And finally, super challenge is in machine learning is some kind of complex tasks like machine translations, chatbots, and so on. This is rather, sometimes it is mathematics, sometimes it is engineering. Mostly it is engineering. But in either case, be it mathematics or engineering, it is far too advanced for our course. So this is something that unfortunately we don't have time to do. So we will learn some basics. But of course, if in future you are going to work in data science or machine learning, then probably you will learn the stuff by yourselves. And finally, a little quiz for you.